talk about big quiz tomorrow coming up. And I got some light. So it's going to be on the big quiz. Big quiz, the last big quiz ended just before rational functions. And so that's where we're going to start. So section 2.6, rational functions. Then we had exponentials after that. Then we started in with logarithms. And then we just ended last week with properties and rules of logs. So those are going to be the 4 sections that are going to be on the big quiz. Relevant ICs, we've got IC 11, IC 12, IC 13, and IC 14. All good study guides. And then the WebAssigns were, this one was A 2.5, this one was A 3.1 part 1, this one was 3.1 part 2, and then the 3.3 assignment has like 2 of them. It says A 3.1 or 3.2 and 3.3. It's actually one assignment, and the title has both those in it. So take a look at those as well. Any of the written homework assignments, since the written problems are out of the book, also good study guides. I don't know any of those off the top of my head. Just so go back and check like the relevant weeks at whichever, anytime we did any of the homework problems from any of those sections. It's going to be good study guides as well. Any questions on that? So office hours tomorrow before the big quiz, 6 to 7. Come if you guys want any help, want to just practice and warm up before you get started on it. Today, we're going to continue with exponentials and logs, and now we're going to throw them in equations. So we're going to do a bit more problem solving with exponentials and logs. So we'll have some extra steps to do, but again, all of our basic algebra problem solving is still going to apply. So our goal and with a lot of these is to just get rid of the exponentials or get rid of the logs to turn it back into a polynomial or a rational expression that we can then solve. So we're just going to start off with some examples and progressively work our way up in difficulty. First example, we've got 3 to the 5x minus 1 in the exponent is equal to 7. And so what we want to do with this guy is apply a suitable base logarithm to both sides. So maybe let's write down some tips for problem solving. So tips for exponentials. So step 1 is going to always be to isolate exponential on one side. And let's say or both sides for the one-to-one property. And we'll see this in an example. This one isn't going to quite apply to this current example. Because the current example, we've already isolated the exponential on one side. When it's this, we're pretty much good. We only have essentially one step to do before I can now get back to polynomial problem solving. Sometimes we've got some extra constants we need to add, subtract, multiply. Sometimes there's a constant out here being multiplied, so sometimes you got to divide it. Once you've isolated the exponential, we're going to apply a suitable log. And I'll say and simplify. And then step 3 is just going to be a solve. I'll explain a little bit more what I mean by a suitable logarithm. Simplification is essentially going to be using these properties of logs that we've been talking about last week. So in this case, what is our suitable logarithm? We have a base 3 exponential and nothing else. I can't solve this with our previous methods. That might be the first thing you want to look for. But 7 is a prime number. 3 is a prime number. I cannot write 7 in terms of a base 3 exponential, at least not easily. So what we want to do is use our properties of logs. And since we have a base 3 exponential, we can go ahead and apply a base 3, excuse me, a base 3 logarithm to both sides. So just like multiplication, division, subtraction, whenever we're doing something to one side, we got to do it to both sides of the equation. In this case, we are going to be applying a log to both sides. And this holds because of the one-to-one property. Same thing with exponentials. I can exponentiate both sides because of the one-to-one property of exponentials. I'm not going to get any extra solutions by applying these operations to both sides. And that helps us to solve these because logs and exponentials essentially undo each other, right? They are inverse operations. So we can actually use properties of logs if you'd like, which will demonstrate sort of future techniques we're going to do. We have a 5x minus 1 in the exponent. Exponentiation inside of logs turns into multiplication outside of the logs. On the right, we just have log base 3 of 7. Log base 3 of 7 is a number, just a number. Think of it like square root of 2. We can type it in a calculator and compute it, but every single time you see these log base constant and the argument's a constant, think of it as a number. It is a kind of a wonky number. We can't get a good numerical estimate for it. And it can throw a little bit of curveballs at us in terms of how we solve these problems. But remember, it is just a number, and the x is what we want to solve for. So nicely enough, when we applied our log base 3 in the bases of the log and exponential match, log base 3 of 3 is just 1. So on the left, we really just have 5 minus x, 5x minus 1. And on the right, we've got log base 3 of 7. And now we just solve for our x. Unfortunately, even though that is a number, we have to write it like that. Similar to like the quadratic formula, right? When we have 1 plus or minus square root of 17 or something like that. We just keep it as is, and now I divide everything by 5. And that is our solution. We can type that in a calculator or a program and have it compute a numerical approximation for us if we wanted. So our second example, just a little bit harder, maybe one tiny step. We've got e to the 3x plus 8 on the outside of the exponential is equal to 12. So remember the steps. Our first step, we want to isolate the exponential on one side, or sometimes if we have exponentials on both sides, we want to essentially isolate both of those if we can. So we'll have e to the 3x is equal to 4. Now, once we've isolated the exponential term, where the variable is, we want to apply a logarithm to both sides. And in this case, the base is e. So we're going to apply a natural log to both sides. Got natural log of e to the 3x equals natural log of 4. And natural log of e to the 3x is going to simplify to just 3x. Again, you can bring down the 3x if you want, and then realize natural log of e is just 1. Or we can realize that log base e of the exponential are essentially going to undo each other, and that we are simply reduced to whatever the argument is of the exponential. And on the right, natural log of 4, just a number. And so solving, we get x is equal to natural log of 4 divided by 3. So our third example with exponentials, it's going to be 3 to the 2x plus 1 equals 5 to the x plus 3. And I want to do this two different ways. So if we look at the tips, we want to isolate the exponential if we can on one side, but in this case we can't because we have two different exponentials. So in this case, about the best we could do if we wanted one exponential, I could divide by it, but it's going to be a little weird. It's fine still to have exponentials on both sides of the equations as long as we're not adding and subtracting. That addition and subtraction will get in the way. Multiplication isn't too bad, even if there's extra constants hanging out. You really want to try to simplify and reduce it as much as you can. And with this problem, it is really reduced. We can't put all the exponentials on one side because they are different bases. And so now that kind of brings up the question, well, what do we do? What is the suitable log? Right? Step one, there's nothing more to do. Step two, we want to apply a logarithm to both sides. But I've got two different bases. So what's the best one to choose? So let's put a star, put an asterisk. Actually, it's true that any base logarithm will work. In any of the problems we just did, either of those two, even though the first one was nice to choose a base 3 because the exponential was base 3. It was nice to choose a natural log because the exponential was an e. We could actually use any base logarithm for either of those problems. We could have used log base 10 for both of them. And so same thing here. I can actually use any base log. It'll work. The only caveat is you want to be careful with the algebra, and I'll show you why, because we'll do this two different ways with base 3 and then a base 5. and we'll show how you get the same answer, but there's a lot of algebra and a lot of work to go from one answer form to the other. So a tip I would give to you guys on tests and quizzes, especially since they're all multiple choice, that you may want to look, if you get something like this, look at the answers beforehand, see what base logarithm the answers are in. If the answers all have like log base 2 of something, you're going to want to use log base 2s in your problem solving. If they're log base 5s, you're going to want to use log base 5s. It's only going to be problematic is if there's different answers with different bases. And then I would, I would probably start with whichever base appears most. If most of the answers have log base 3s, you may want to check that first with your problem solving. But it is kind of throwing a wrench at you because any base log will work, you can get the correct answer that just looks differently. It's like the difference between writing square root of 2 versus 2 to the 1/2 or something like that. They mean the same thing. They just look a little different in the way they're written. So let's go ahead and solve this, and let's see what happens when we apply log base 3 to both sides. We will have log base 3 of 3 to the 2x plus 1 equals log base 3 of 5 to the x plus 3. On the left side, this helped. The logs and exponentials undo each other, and we're just left with 2x plus 1. On the right, though, the logs and exponentials do not entirely undo each other because they are different bases. We can still use the property that exponentials or logarithms turn exponentials into multiplication. The x plus 3 came down as multiplication outside of the log. And now we just have log base 3 of 5, which is a number. But now we got to solve this. And solving it, you just got to be very careful. The techniques are still the same. We want to isolate our x's. And so if I distribute this log base 3 of 5, we'll get x times log base 3 of 5 plus 3 times log base 3 of 5. We subtract all of the x's to one side of the equation times log base 3 of 5 is equal to 3 log base 3 of 5 minus 1. Sorry, that was a times there. So we only have x's times constants on the left, meaning I can factor out this x. And when I factor it out, we are just left with 2 minus log base 3 of 5. And then we divide. And that is our answer. Again, these are just numbers. We can type that into a calculator and it will compute the x value for us. It'll approximate it for us with the decimal. Okay, so let's try this the other way. What happens if I use log base 5? Just for practice, it's going to be good to go through those steps again. And if we apply log base 5, The right side's nice. It'll just simplify to x plus 3. But the left side will move down the constant, or the exponent as a constant out front. And we're left with this multiple of log base 5 of 3 that we'll have to distribute. So we see how logs help us no matter what the base is, because they move the variables that are in exponents out front in terms of multiplication. And now we are just back to straight polynomial problem solving. So distribute the log. I'm going to write it as 2 times log base 5 of 3 times x. So our 2 times log base 5 of 3 is the multiple of x, plus log base 5 of 3 equals x plus 3. We want to isolate all the x's. So I'm subtracting that x over. And then on the right, I will have to subtract log base 5 of 3. Once we've got all the x's, I'm going to factor that out. So we're left with 2 times log base 5 of 3 minus 1 is equal to 3 minus log base 5, 3, and then divide. And so now the question is, well, how does this compare with the first answer we got? So does this equal 3 log base 3 of 5 minus 1 divided by 2 minus log base 3 of 5? We did the problem the same way. We just used 2 different logs. And I claim that these 2 answers are exactly the same. They just look different. And so how can we check this? How can we check if we got the right answer? The thing we have to do is change the base of the logs. So remember, our change of base formula was log base b of x is log base c of x over log base c of b. So let's take the second answer we got. Let's try to change the base of these logs to log base 3, and then see if we ultimately end up getting the answer we solved for using log base 3 from the get-go. The algebra is going to get a little messy, so let's see. We've got a 3 minus log base 5 of 3. I want to change to a log base 3. How do we do that? It's going to be a log base 3 of 3. So change the base, keep the argument the same, but divide by, change the base, log base 3 of the old base. Put the old base in the argument on the denominator logarithm. So log base 3 of 5 goes down there. So that's our numerator. We'll then divide by 2 times. Again, we'll have a log base 3 of 3 divided by log base 3 of 5, and then still that minus 1. an equal sign there. Okay, well, that looks kind of closer. Got the log base 3's in there. All these constants are kind of looking the same too. How do we simplify this now? We've got a compound fraction. These are some good skills to work on, since we spent a couple days on rational functions, but a lot of time graphing rather than manipulating compound fractions is what I call them, fractions within fractions. This is an important skill to have, especially for calculus, because you'll get quotient rules and L'Hopital's rules and all sorts of other operations that you do in calculus where you'll arrive at fractions within fractions, and then you're going to want to simplify those. You never want to leave answers in such a form. So what you want to do is you want to think of the numerator denominator across the big denominator with a big division sign, sort of as entities of themselves. And what do we want to do? We want to multiply and divide by a constant. So let's actually multiply and divide by the base of this log. So it'll be log base 3 of 5 divided by itself over the big denominator. We're just changing the expression. Multiplying by 1 isn't going to change with a value, just change the way it looks. And then when I distribute this, so this is in parentheses here in my numerator, I'm now multiplying this entire expression by log base 3 of 5. When this distributes here, it will cancel out with that denominator, and it just also has to distribute there. So in the numerator, we will be left with 3 log base 3 of 5 minus log base 3 of 3. What is log base 3 of 3? Just 1. Do the same thing in the denominator. I got to distribute this guy to this term, but the log base 3 of 5 will cancel out that guy. So in the denominator, we'll just be left with 2 times log base 3 of 3, which is 1. So 2 times 1 minus, and then I got to distribute this guy to that negative 1. And so we are left with this expression, which is what we found doing it with a log base 3 from the beginning. So just a little warning on that. You can get different answers that look different, but they are still the exact same value. And if we wanted to check it further, if we typed both of those in a calculator and computed them, we would get the exact same result. But tests and quizzes, the answers are going to look like this. You know, they'll have logarithms in the answers. So you want to be careful with that, with how they look and how your answers look. It's just an extra wrench thrown into this problem-solving method. So just because you do a problem doesn't necessarily mean you did it wrong. Could just mean your answers look different. Another thing to keep track of. All right. So let's take a look at now logarithmic equations. So these were equations where I have exponentials equal to each other. What happens when I have logarithms equal to each other? So I'll start off with some easy ones. This is number 4. We've got log base 3 of x equals 4. So similar tips. We're going to isolate the logs. Either on one side or on both sides. For the one-to-one property. Step 2. So step 1 is essentially already done for us. We've got our logarithm isolated. The variable is inside of a logarithm, so we got to get it out. And that's going to be our step 2, is going to be exponentiate both sides, or rewrite the equivalent exponential equation. So actually, if we have logs on both sides, exponentiating might be easiest, or just using the one-to-one property where we can essentially declare the arguments of both sides equal since logs are one-to-one. Or we can use this equivalent exponential statement. So what do I mean by that? Remember when we first introduced logs, I think it was last Monday, a week ago? What does this statement mean? It's always 3 raised to the opposite side, so 3 to the 4th equals the argument of the log. That's what I mean by the equivalent exponential statement or exponential equation. Bases are the same, so base of the log always the base of the exponent raised to the opposite side of the equation equals the argument. So these two equations imply the same thing. And that solves for x for us. The other thing you could have done is to exponentiate both sides. So meaning if I take 3 and raise it to both sides, now we can essentially say that because the base of the log, the exponential and the log, they're touching each other, right? They're the same base, and these operations of exponentiating and then logarithm undo each other, so they cancel, and we're just left with x equals 3 to the 4th, or 81. So however you want to solve that. I kind of like this way a little bit better just because it's quicker, but this way is also not wrong. And I guess third step here, solve. Not much for us to solve here. Sometimes they'll get a little bit harder. Let's do another one. Let's do log base 3 of x minus 1 equals 2. So our log's already isolated. I can exponentiate both sides or rewrite our statement. This means 3 to the x, or excuse me, 3 squared equals x minus 1. And so we will get 9 in our last step of problem solving. Add the 1 over. So x equals 10. Nothing too tricky there. Sometimes you'll see these problems. Not often. They come up occasionally, though. There's always going to be a few, maybe on WebAssign, where now our variable is in the base of the log. Log base x of 3 equals 4. It asks, what base do I need so that when I apply a logarithm of that base to 3 and get 4? And this is where I really like to just rewrite the exponential statement. Base is x, so this just says x to the 4th equals 3. And then we got a polynomial. So x is equal to 4th root of 3. Or if you want to write it, 3 to the 1/4. Either way. Okay, so far not too bad. Let's do one with a little bit more work involved now. So let's say we've got natural log of x plus 2 plus natural log of x minus 6 equals natural log of 3 minus 2x. So let's take a look. Step one, we always want to be able to isolate the logs, or we need both sides of the equation to just say log of something equals log of something. Then we can use the one-to-one property. So I'm going to give you guys a warning. I'm going to write it big. Don't do this. Why is this wrong? A lot of people really want to jump into to exponentiating both sides. It's once we exponentiate both sides, as we saw in these previous problems, reduces down to solving a polynomial. However, you got to be careful with how the original equation is written. Sometimes we've got some work to do in isolating these logs. The right log isolated on this side of the equation. But this one, there's a plus outside. Neither of these logs are isolated by themselves. We're operating between them by addition. And this statement is not true. It's that plus there that is wrong. Why is that plus wrong? Because when we exponentiate both sides, when I apply an operation to both sides, we would have to apply it to the entire sides as they are written, meaning the correct statement would be e to the natural log of x plus 2 plus natural log of x minus 6 is equal to e to the natural log of 3 minus 2x. This is a true statement. The addition has to be upstairs with the logs in the exponent. And so if you do it this way, you'll get these exponentials and logs. You'll say, oh, they undo each other. But then when you solve the remainder of this, you'll get a wrong answer. Now, this is correct. However, it's not too nice. I don't like to solve things from here. You can if you understand how to manipulate this expression and how to deal with that sum. But I would prefer not to even go this route yet. I would prefer myself to solve the problem. And actually, I would kind of prefer most of you guys to solve it in the way which I'm about to do. So let's box this guy off. And let's rewrite this so we can do some of the work and do it the best way. So natural log of x plus 2 plus natural log of x minus 6 is equal to natural log of 3 minus 2x. This is what we had. This step one of isolating these logs or having it as log equal to log on both sides, isolating our logs, we want to use all of our properties of logs. So everything we've been developing over the past couple days, over Wednesday and Friday last week, we want to combine our logs and write them as a single logarithmic expression. So whether there's constants out front that we need to put up in the exponents, or if there's addition or division outside of the logs that we can then combine as multiplication or division inside of the logs. Let's start with those steps. So this says natural log of x plus 2 times x minus 6. Addition outside the logs, multiplication of the argument inside of the logs. And that multiplication is of the entire expression. So the entire arguments. So we will have to distribute this eventually. But now what we've done is, even with just that one step, we have isolated log on the left, log on the right, and that's all there is. Log of something equals log of something. And those logs have the same base. So now they have the same base. If we exponentiated both sides, that would undo the logs. Or we could just cite the one-to-one property of logs and say that if two logarithms of the same base are set equal to each other, then this means that the arguments now inside of those logs have to be the same. So we get x plus 2 times x minus 6 is equal to 3 minus 2x. And now we've reduced the problem back to a quadratic. So let's go ahead and get through that real quick. Distribute this out, we will have an x squared. I will have a plus 2x and a minus 6x. So that'll give me a negative 4x minus 12. Right side, nothing to do. Let's go ahead and add the 2x. So we will have x squared minus 2x. Subtract the 3 until we get a negative 15. Now we've got a quadratic equal to 0. You can use a quadratic formula if you want. You could use completing the square. But again, I almost never recommend completing the square, since the quadratic formula gets the exact same thing as that quicker. Or best method, look to factor. So we should have x minus 5 times x plus 3. So we get x equals 5 and x equals negative 3. Are we done? I claim no. Let me actually add one more note. I don't have a whole lot of space for it here. So solve. I'll put 2 stars and say check. Always check your answers with logarithmic problems, especially if there's quadratics. If there's linear factors inside of the arguments, checking isn't too bad. It'll almost never go wrong. Actually, I don't think it can go wrong when there's only one log and just a linear power of x. Nothing too bad can happen. However, even though these are linear factors, what happened when I used this property of logs to combine them? I all of a sudden now have a quadratic equation that we're solving. So if you end up with something like a quadratic and you start to get multiple answers, whether it's quadratic, cubic, or any higher power polynomial, even rational functions, always check. And primarily, we want to make sure that the answers are still in the domain of the original function, because natural logs and logs are one-to-one functions, but quadratic functions are not. So sometimes we'll get extra solutions out of these quadratics that all of a sudden now don't quite make sense in the original functions. So for example, what's going to happen if I plug in 5? I plug in 5 here and we'll get natural log of 5 plus 2 is 7. That's fine. What happens if I plug in 5 here? We'll get natural log of 5 minus 6, which is natural log of negative 1. And that's not in the domain, right? I cannot compute natural log of negative 1. So we got to throw that answer out. So we check the other answers. But it looks like we're going to run into another problem. What happens if I plug in -3 up here? We're in here. I'll have natural log of -3 plus 2 is still -1. We cannot have natural log of -1. Likewise here, natural log of -9. Doesn't make any sense. So we actually have to throw this answer out as well. So what happens when we end up in a situation like this? Sometimes one of the answers will work, and be very careful. It's not that negative x cannot be negative. Sometimes when x is negative, it'll be perfectly fine. Remember, we have to plug in the value into the argument, and we have to take into account for these shifts or even scalar multiples and check to make sure that the resulting expression inside of the log is bigger than 0. And then, of course, sometimes we check both of the answers, and no matter what number we plug in, one of the natural logs, at least, is going to bug out on us. It's going to be a natural log of a negative number. And so we have to throw those out. And in this case, it's just no solution. Any questions on that? All right, so we'll stop there for today.